Hi everyone, thanks for coming to see my presentation in this format. My name is Daniel Ward and I am a PhD student at the University of Leeds. My supervisors are Sam Pegler and David Ferguson, also from Leeds, and Som Dutta from Utah State University. If you need to contact me, my email address is on this slide. I'm going to be talking about the dependence of plumes on viscosity, specifically looking at the rise height and the dependence of the plume on Reynolds number. So firstly then, a plume is a buoyancy-driven flow emanating from a convective source. In an unstratified environment, a plume consists of a plume stem and rises pretty much indefinitely. When a stratification is included, this introduces a neutral buoyancy level. At this level, the plume's buoyancy goes to zero, and this causes the plume to spread laterally outwards along a horizontal plane. Prior to this, however, when the plume reaches its neutral buoyancy level, it has some momentum left over, so it overshoots and goes to its maximum rise height before falling back down to its neutral buoyancy level. Plumes are very common in nature and can be found across a huge range of scales. For example, we've got some plumes at small scales here, or small Reynolds numbers in this case, and examples of these are plumes generated by humans or candles or any small heat source, like a radiator, something like that. Understanding the behaviour of a plume on such a small scale is important for applications in something like natural ventilation, which is especially significant considering the current COVID-19 scenario. At the other end of the spectrum are volcanic eruptions. Understanding the behaviour of these plumes is critical for predicting the dispersal of volcanic ash and harmful particulates generated by a volcanic eruption. So we have plumes across a huge range of scales, and plumes have been studied widely in the past. One of the first notable studies was by Morton, Taylor and Turner in 1956. Their model, which is often referred to as the MTT model, models a plume in terms of its volume, momentum and buoyancy fluxes. It's a fairly simple but useful model, which has been studied extensively by many subsequent authors. The MTT model uses an entrainment assumption to close the equations and therefore does not take into account the Reynolds number of the flow. And for some applications, such as volcanic eruptions, where the Reynolds number is something like 10 to the 7, 10 to the 8, 10 to 9, they don't need to. As I will show you later, there exists an asymptotic regime in the high Reynolds number spectrum whereby an increase in the Reynolds number no longer has any further effect on the bulk flow dynamics. One, for example, in this case that we're looking at is the rise height. However, if one is considering plumes at a lower Reynolds number, for example those in a laboratory setting, the effect of the much lower Reynolds number could actually play a very important role in the dynamics of the plume. It is this dependence of a plume on the Reynolds number that I'm investigating in my work, and I'm doing this using numerical simulations to model plumes. So there have already been some numerical studies of plumes, and in these they often pick a high Reynolds number and then say that their simulations are sufficiently turbulent. And it's a completely valid approach. I don't want to say anything bad about any of these studies, but what I am saying is that the Reynolds number they picked may not have needed to be as high. They were sort of going over the threshold and sort of wanted to play safe. This therefore may have led to their simulations being more computationally intensive than required. For example, for a volcanic plume study, a Reynolds number of 2000 may produce the same bulk flow properties as a Reynolds number of 7000. But 7000 may be picked just so that the author is certain. In that case, performing simulations at such a high Reynolds number would still produce correct results, but they would take more time and computational power to achieve. This leads me to my research questions. So the first question we wish to answer is what Reynolds number is low enough to capture sufficient plume dynamics? And then more broadly, what is the effect of Reynolds number on the flow? In this study, we've picked the right height of a plume as an indicator, and so we ask, what is the right height of a plume for a given Reynolds number? And as is often the case in research, we uncovered a further question, which I'll come to later, which is, at what height does a plume go unstable? You can see in the false colour images of a candle that the plume is laminar for a time, and then goes unstable at some height above the plume source. So how am I going to answer these questions? Well, I've been using 3D direct numerical simulations, or DNS, of plumes, and I'm using the spectral element code NEC 5000. Here are the governing equations. They're the dimensionless Navier-Stokes equations reframed in terms of a temperature difference from the stratified ambient. So rather than just calculating temperature, we calculate the relative temperature. The non-dimensionalization, which I haven't included here, results in the dimensionless parameters, the Reynolds and Peclet numbers. To reduce the complexity of the problem, we're sticking to the case of the Prandtl number equaling 1. This forces the Reynolds and Peclet numbers to be equal, and therefore brings the number of parameters to the study, the number of parameters that we're studying down to just 1. So I performed DNS of a number of different plumes and varying Reynolds numbers to attempt to understand the characteristics of how plumes vary with Reynolds number, with a particular focus on the right height of a plume. Here's a showcase of a plume using a passive scaler to track the locations of the plume, or the location of the plume. Initially, the plume is completely laminar, and there is a small amount of vortex shedding occurring near the front of the plume. Sometime after this, the plume reaches a height at which it starts to become unstable, and subsequently transitions into a more common turbulent plume. It then reaches its maximum right height before returning to its neutral buoyancy level and beginning to spread laterally. So that's an example of one simulation. Now let's compare a few different simulations side by side. Here we have 3 different simulations, each at a different Reynolds number. From left to right, they are 200, 700 and 2000. All 3 plumes have some sort of initial laminar region, which for the higher Reynolds numbers terminates in an instability at different heights. The initial propagation speed is very different also, and this seems to be affected by the instability itself. The right height, as expected, also varies for each Reynolds number, and we can see this more clearly on the next slide. Here we have a larger number of simulations with their right heights plotted against Reynolds number. At the higher end of the Reynolds number spectrum, the right height appears to be approaching an asymptote. We have more simulations running to test this further, but the asymptote should inform us of the appropriate Reynolds number required to run a highly turbulent plume simulation. At the lower end of the spectrum, the right height appears to be approaching 0. But as the Reynolds number goes to 0, we know diffusion will dominate any advection, or indeed any other flow property, and we will simply be left with a diffusion problem. Maybe surprisingly, or at least it was to me, there is a turning point at about the Reynolds number 700 point. The plume seems to reach a total maximum right height at this value, and as visible from the previous slide, the stable laminar region appears to be influencing this effect. Understanding the behaviour of this laminar region is therefore quite important. So that brings us to another part of my work, which involves some laminar plume theory. I've used some boundary layer theory to make some assumptions about the flow and simplify the governing equations to those that you can see here. They're also axisymmetric. I then use MATLAB to write a Crank-Nicolson solver to solve these new equations and grab right height from there. The current results are not quite there yet, but you can see from this crude MATLAB plot that the trend is correct, so hopefully it's not too far off, but I guess, well, time will tell. This laminar theory should allow us to predict the right height of laminar plumes. We also hope it will inform us of the height of the instability. Now I'm going to consider a slightly different question, namely that of a disturbance. For some applications of a plume, the laminar region we've been discussing is not desirable. The initial conditions of a simulation are, well, perfect. The source and inlet flow is completely uniform. This is just plain unlikely for something like a volcanic eruption, for example. The approach of some numerical modelers then is to apply perturbation, what we're calling a disturbance, to the flow at the inlet. In this little side study, we attempt to quantify the effect of this disturbance on the flow and its effect on rise height. Looking at the plots on the left qualitatively, we can see a decrease in the rise height as the size of the disturbance is increased. The disturbance appears to disrupt the laminar flow early. We can see this quantitatively on the next slide. Here, the blue line represents no disturbance, the red 20% disturbance, and the green 50%. At low Reynolds numbers, the disturbance doesn't have any effect on the plume's rise height. But as the Reynolds number increases, we can see that the rise height is largely reduced due to the disturbance being applied. There's clearly some important behaviour going on here that should be understood before applying this to our simulations. So to conclude, I'm revisiting the open questions from earlier in my talk. Our first was, what is the rise height of a plume for a given Reynolds number? We answered this for a range of Reynolds numbers and plan to add a few more to the list with subsequent simulations. Our second question was, under what conditions can we model an effectively infinite Reynolds number plume? We believe we can see an asymptote forming to the right of the plot, and again, with a few more simulations, we expect to uncover a more concrete asymptote. Our third question was, at what height does a plume go unstable? This question is currently unanswered, but we expect a result from our laminar theory hopefully quite soon. We also discovered a couple of other interesting things. Firstly, that there is a clear turning point at Reynolds number 700, and that as the disturbance increases for a plume, it decreases the rise height. So the final conclusion of my work is pretty much, I need to do more work. But hopefully you can see that there's some interesting stuff going on. If you made it to the end, thank you for listening, and if you have any questions, feel free to email me or contact me on the APS DFD website.